Hello everyone. In this lecture I want to actually do a certain experiment by which I can explain to you what voltages actually mean to a logic gate. Okay. So before I get into the experiment, let me explain the experimental setup very clearly and tell you what we are going to do very precisely. Okay. So this 7400 is the number of a certain IC, integrated circuit, that has a couple of NAND gates, right. I understand we don't know what a NAND gate is yet, okay, but for all practical purposes, if I connect one of the inputs to the high or the power supply VDD and then I connect another input A and I look at the output Y, this is exactly equivalent to an inverter, okay, an inverter with an input A and output Y, power supply going to VDD and the ground being connected to the circuit ground, okay. So effectively we will be looking at a circuit which is equivalent to this, okay. And now what we want to do is, of course, I also understand that we have not looked at what an inverter means in terms of logic, right, but for the purpose of this discussion, right, we will just go with the English meaning of an inverter, which means if I give a logic low, right, or L, I will get an output 1 or a logic high, okay. If I give a logic high or H, then I will get logic low 0 or L, low, logic low, okay. The idea is to eventually understand what this logic high, logic low means and all that, okay. So the main objective of this experiment is to actually measure and understand what a voltage transfer characteristic looks like, okay. Voltage transfer characteristic, okay, voltage transfer characteristic, it's abbreviated as VTC, okay. So the idea is instead of looking at an inverter, okay, as simply a logical input which could take low and high, we are going to look at this inverter as taking an analog input V in and we are going to look at the output V out again as a voltage, okay. The input V in is swept between 0 and VDD, okay. So VDD, by the way, is the supply that we have used for this, and in this case for this particular IC it is 5 volts, okay. So we are looking at a 5 volt supply and a ground, right. So what we need to do is we want to feed different input voltages from 0 to VDD and then study what the output voltage is going to look like, okay. Now how do you do this? You could do this in multiple ways. You could take a power supply, right, which can be controlled and feed it directly as an input to this input pin A, right, or Vin, okay. Now instead what we are going to do is we are going to use a concept that you studied earlier in the electronic systems thinking course, which is basically the concept of a voltage divider, okay. So I have a voltage here, I have two resistances R1 and R2, this is VDD, okay, and what I am going to do is I am going to feed this intermediate point to my inverter, okay. The inverter has its own power supply which is the same power supply as I am giving to this resistor divider, okay, and this output V0 is what we want to observe, okay. So this intermediate point is actually V in to the inverter's input, okay. Now clearly you can write out KCL, KVL and you will understand that V in is simply R2 divided by R1 plus R2, okay. We are assuming that no current goes into the inverter, okay, and into VDD, okay. So if I can change R2, right, if I can sweep R2 from all the way from 0 to a very high value, then effectively my input would actually go from 0 to VDD, okay. So how is this achieved? This is achieved with something known as a potentiometer, right. So there is a potentiometer which I will show you later in the experimental setup, which allows you to do this. So there is a screw which if we turn, right, you will see that the resistance of two of those terminals, right, between two terminals will change, right. So a potentiometer effectively is something like this. It's a small blue color square looking thing with three terminals, okay. So the three terminals are what you give to VDD, okay, what you give to ground, and the third terminal is what you are going to control in Vn. So there is a screw here. If I change the screw, then the resistance R2 will change with respect to R1 with respect to the total resistance R1 plus R2, and you will get a different voltage for every position that I keep the screw in, right. So this is the fundamental thing that we are going to do. And of course now I need to also measure Vn, because by changing the screw I do not know how much the resistance is changing. So what I am going to do is I am going to feed this to your voltmeter or multimeter, right, multimeter, which is going to measure a voltage for me, okay. And now assuming that you have only one multimeter and a kit, right, like the ADALM 1000 or something like that, or some other hardware kit that can give you signal generation, oscilloscope and all that, I am going to feed this to channel A of my kit, okay. In this case I am using the analog discovery kit, but you could use any other kit also, okay. So one input is going to the multimeter, the other is going to the channel A of the kit, okay. So the idea now is we are simply going to vary the resistance by tuning the screw, okay, measure the voltage V in, okay, and then observe what is going to happen to the output voltage, right. So first of all, we already have some fair idea, because the power supplies are between 0 and VDD to this inverter. V out will also be contained within 0 and VDD, okay. So this is the expectation. This also has to swing between 0 and VDD at most, right. This is the upper bound and lower bound is what we are saying. So what we can do now is to go ahead and look at the experimental setup out here. So what we have here is the experimental setup, okay. I have my kit here, which is of course connected to the USB on one side, and channel A is being connected to this IC, okay. So the black IC that you see connected into the breadboard is the 7400 IC, okay, and this blue color component that you see here is the potentiometer, and the screw that you see here is the screw that I was talking about, which can be used to tune the resistance, okay. Now I have the multimeter here, which has been configured to actually read out a DC voltage, as you can see from this setting here, right. In fact, you can already see that it is reading some value of 172.7 millivolt, right. So what we are going to do now is we are going to essentially vary this voltage, right. We are going to vary this screw here, and we are going to tune the screw and look at the voltage that is appearing on this multimeter, and the output voltage is going to be available through this kit on channel A of the oscilloscope, right. So, if I look at this, so what you see here is the orange color line, and you must focus on the y axis in orange on the left, which is channel 1. It says in volts. Currently the output voltage is reading a DC value. There is some noise, but it is reading a value of 5 volt. It is between 4 and 6, exactly halfway between 4 and 6, and therefore you basically are reading a value of 5 volts. Okay. So now the idea is for us to go ahead and start varying this voltage, right, from somewhere close to 0 all the way to 5 volts. Okay. Now we can't do this in very fine steps, so we'll just look at a couple of readings in the important regions, okay, as I will explain to you in a couple of minutes, right. So let's look at what happens. So right now my input voltage V in as read by this multimeter is reading 172.6 millivolts, right. It is about 0.17 volt. That means we are closer to ground, and the output that seems to be coming out of this inverter seems to be 5 volts. Okay. Ignore the channel 2 in blue, okay, because that is not used in this experiment, right. So therefore do not look at the y axis on the right, look at the y axis on the left here, that reads 5 volts. Okay. So now I am going to go ahead, okay, and then slowly start increasing, turning the screw in the clockwise direction. You automatically see that my input voltage, right, as read by the multimeter has gone up to somewhere near 0.45 volt. I am now closer to 0.5 volt. Okay. So I will probably take a reading somewhere here. At 0.5 volt the output is still reading 5 volts, okay, and then I am going to continue further like this. Okay. I continue going in the clockwise direction. So remember, when I turn the screw clockwise, the resistance inside is changing, right, and the partition of the resistance is changing, and thereby the voltage divider is giving me a different voltage for every position of the screw. So from 0.5 volt I will jump directly to 1 volt. Okay. So somewhere close, yeah, right, somewhere near 1 volt. What you see is the output is still unchanged, right. So we did 3 things: 0.17 volt, we did 0.5 volt, and then we did 1 volt, right. And what we have observed is all this while the output is still 5 volts, there is no change, right. So I am going to go further, right. Now I am going to go until the point I start seeing the output drop, at some point. Remember, this is an inverter, right. So if I give logic 0, I should get 1. So close to 0 means I should get an output of high, logic high, which is 5 volts, and that is what is happening here, right. So I continue doing this, okay, and I am going. So you see I have gone all the way nearly to 2 volts, right. I am now closer to 2 volts, right, and the output is still stuck at 5 volts, right. So an input range of 0 to 2 volt gives me an output of 5 volts, it is constant at 5 volts. So now I am going to continue this until the point I start seeing the output drop a little bit. So you see suddenly the output started dropping, okay. So I am going to now go slowly here, somewhere near 2.6 volt the output has dropped, okay. I am going to go back You see this, it's struggling somewhere there. So I'll just hold this voltage somewhere at 2.539 or 2.540, right. At around 2.5 volts, the output has dropped to something like 3.5 volts, right. The output has dropped to 3.5 volts, right. So this is what I am going to do now, okay, and maybe what I will do is I will just make a note of this before I proceed any further, right. So I am looking at V out in volts as a function of V in, or maybe I should swap this, V in, V out in both in volts. So 0 to 2 volts output was 5 volts, okay, and even at 2.538 volts the output is at 3.5. So it has dropped to 3.5 volts, right. This is 5.0, right. So now what I do, I continue this process, okay. Let me go back to the oscilloscope here because I have to observe that. Yeah, so yeah, somewhere near 2.7 volt the output has dropped to 3.2 volt, okay. I am going to just make a note of this again. This is 2.7 volt, this has dropped to 3.2 volt, right. Then I continue further. You can see that the output is dropping, right. So here I am going to go a little carefully, I am not going to jump, you know, in steps of 0.5 volt or something. At 2.8 volt we are, no, I will just increase it, I will get the output down to something like 3 volt. Yeah, right, at 2.855 volts, right. So 2.855, the output is close to 3 volts, right, as you can see from the marking here, right. Now I continue this experiment. I am going to do it, take it to 3 volts. Yeah, this is somewhere near 3 volts. Yeah, 3 volts, and the output is about 2.8 volts, okay, 5 divisions there, so each is 0.2. So at 3 volts I get 2.8 volts, right. Then further at maybe 3.2, yeah, 3.2 volt, my output is 2.6 volts nearly, okay. So what is this, 3.2, 2.6. So what you are observing is now for every 0.2 volt increase the output seems to be falling much faster, right. Earlier it was just stuck at 5 volts, okay, but now it seems to be falling much faster, okay. So now you come back here and you continue doing this, right. Now now again there has been an abrupt change, so I will go slowly again here. Yeah. So what you see is, I mean, there might be, it might be hard to get some measurements in that region, but beyond 3.5 volt again, right? If you look at it, I'll go to 3.5 volt, the output sort of fell drastically down to 0. Okay. So you look at this output here, it's now stuck at 0. Okay. And I continue increasing my input voltage. As you can see, I can just take this all the way to 4 volt, closer to 5 volt, and you will see that the output is sort of stuck there. Okay. But then I continue to go anti-clockwise, which means I am going to reduce the input voltage again. Okay. Right, just to show you that the output can eventually go back. Yeah. So somewhere near 2.7 volt, it is close to 2.5 volt, right? So here somewhere near 2.7 volt, the input and output seems to be equal. Right, I am back now here, yeah, back to 2.2 volt somewhere, it's back to 5 volt, right? Essentially that is what the experimental setup is telling us, right? So you take an IC, it's supposed to be a logic inverter which gives logic, if you give logic 0 you will get logic 1, or you input logic 1 you will get logic 0, but what's happening is you are actually getting a voltage. Okay. So the idea is to understand this voltage transfer characteristic and explain the characteristics accordingly in the theory as well, right? So let's look at this, this plot that we have here. Maybe what I'll do is I will just take this data here from here with me, okay, and then go to the next page. This is the experimental data. So if I were to plot this approximately, right, I am looking at V out in volts as a function of V in volts, okay, and we also had another reading, I would say 3.5 to 5 volts, right, we went up to 4.5 I think, right. So I will not go beyond that. Says 3.5 to 4.5, it seems to be going to 0 volts, okay. So let us first of all look at something like we have 5 volts here, okay, this is 2.5, right. So let me look at 1, 2, 3, 4, right. So this is 1 volt, 2 volt, 3, 4, right. Somewhere near 2.7, this is 2.5, right. Somewhere near 2.5 you have the output, almost close to the input, okay. V out is almost equal to V in, somewhere near 2.7, right. I will not worry about the exact number, but you see that the output is constant almost from 0 to little before 2.5 volt, right. So let me just draw that, right. On the other hand, after 3.5 volt, which is somewhere here, the output again is absolutely constant. In this period between, so somewhere near 2.538, so somewhere just after that, the output dropped again 5 volts, right, 4, 3, 2, 1, okay, 1, 2, 3, 4, right. So somewhere near 2.54 volts it has dropped to 3.5, right. So somewhere here, right. Then at 2.8 it has dropped to 3, which is 2.8, somewhere here it has dropped to 3, right, and then 3.2 it has dropped to 2.6, somewhere here. These are the measurements that we have. We have to interpolate now between these points, right, and it is something like this, effectively some curve like this, right. In reality you will not have sharp edges in any system like that, it would be sort of smoothened out, okay, but the measured experimental results seems to be suggesting that the voltage transfer characteristic is like this, okay. So this is your VTC, okay.